All right, so get ready because today we are going deep, really deep into set theory.
Oh, wow.
Yeah, and I know it doesn't sound maybe like the most exciting thing,
Yeah.
but trust me on this one. This is going to be a really fascinating deep dive.
Okay.
We're looking at the Stanford Encyclopedia of Philosophy's take on set theory.
Okay.
And, we're going to be exploring all these like big philosophical questions like infinity
Right.
and, existence itself. Like, what does it mean for something to exist?
Yeah.
So have you ever wondered like what it truly means for something to be infinite or how we even like begin to understand the world?
Mm-hmm.
Well, set theory, it offers some surprising and sometimes really challenging answers.
Absolutely. I think what's really fascinating about set theory is that it starts with a seemingly simple idea.
Okay.
Like a set, it's just a collection of objects.
Yeah.
But from this very basic idea, a whole universe of thought kind of gets constructed.
Right. It's like a seed
Yeah.
that grows into this huge tree.
And it's a universe that is full of really profound insights.
Yeah.
And yes, some really tough paradoxes.
Yeah, exactly. And that's what we're going to get into today.
Yeah.
So the Stanford Encyclopedia really traces like the history of set theory back to the work of Georg Cantor.
Mm-hmm.
And this was like in the late 1800s.
Yeah.
And what really captivated him, you know what it was?
What's the...
Infinity.
Right.
Yeah, infinity. So before Cantor, infinity was this kind of like vague and even mystical,
We can say that again?
like this almost like untouchable concept, right?
Yeah.
But Cantor, he like brought it down to earth
Mm-hmm.
by giving it a really like rigorous framework.
Right, a mathematical framework.
Yeah, exactly. He made it like something we could actually like study and work with.
Yeah, and what he discovered was revolutionary. I mean, absolutely groundbreaking.
Okay, I'm ready. Hit me.
Okay, so some infinities are actually bigger than others.
Wait.
Yeah.
Hold on. Bigger infinities.
Wow.
I thought infinity was just, well, infinite. Right. Like, how can you have one that's bigger than another?
Right, and that's the question that initially puzzled mathematicians and philosophers alike
Understandable.
because it seems counterintuitive.
Yeah.
But let me give you an example, okay? Think about the set of all natural numbers.
Okay.
So 1, 2, 3, and so on, forever.
Okay. Yeah. It goes on forever.
Infinite, right.
Totally.
Now consider the set of all real numbers.
Okay.
This includes not only the natural numbers, but also all the fractions,
Okay.
the decimals, all the irrational numbers like pi,
Yeah.
square root of 2, all that stuff.
Okay.
Both sets are infinite.
Yeah.
But the set of real numbers is kind of denser.
Denser.
Yeah, more tightly packed.
Okay. I think I see where you're going with this. So it's like
Yeah,
the real numbers are kind of like a richer, more expansive infinity
you got it.
compared to the natural number.
Yeah, but precisely.
Okay.
And Cantor proved this rigorously.
Mhm.
He showed that there's no way to pair up each natural number with a unique real number
Yeah.
without leaving some real numbers out.
Oh, interesting.
So this means that the set of real numbers has a larger, what we call cardinality.
Okay, there's another one, cardinality. So
Yeah.
that's how in set theory you measure the size of infinite sets.
Exactly. It gives us a way to compare them and to rank these different infinities.
And this is like a huge discovery, right?
Oh, absolutely. It changes everything.
Yeah.
It throws a wrench into our intuitive understanding of infinity.
Yeah.
Because if there are different sizes of infinity, what does that tell us about the nature of the infinite itself?
Exactly.
Does it mean that there's a hierarchy of infinities?
Whoa.
Maybe even a biggest infinity?
Right.
These are the kinds of questions that have kept philosophers busy for centuries.
Yeah. And that kind of brings us to one of the biggest mysteries in set theory, right?
Yeah.
The continuum hypothesis, which the Stanford Encyclopedia, they really highlight how this is an unsolved problem.
Yeah.
That's been haunting mathematicians for over a century.
It's a big one.
Right. So tell me more about this continuum hypothesis.
All right, so the continuum hypothesis, or CH for short,
Okay, CH.
it asks a deceptively simple question.
Okay.
Are there any sizes of infinity
Mm.
between the cardinality of the natural numbers
Right.
and the cardinality of the real numbers?
Okay, so
Well,
are those the only two rungs on the ladder, or are there more in between?
right. Are there more levels to this infinite climb?
Yeah.
And the answer is,
Drum roll, please.
we still don't know. We don't know.
That's crazy.
It's wild.
So it's we've got this
Yeah.
set theory gives us this whole playground of infinity,
Mhm.
and then it's But here's this one question.
Yeah.
We don't know.
We can't answer it.
It's like a giant tease.
It is. It leaves mathematicians and philosophers just scratching their heads.
Yeah, and I'm sure you've been scratching your head about this.
Oh, for a long time.
So, but it doesn't stop there, right?
Yeah.
The journey of set theory, it's not just about infinity.
Right.
It gets even more interesting, maybe a bit dangerous, I don't know, when we encounter those like mind-bending paradoxes.
Right.
So the Stanford Encyclopedia mentions this idea of naive set theory.
Mm-hmm.
So what goes wrong there?
Well, naive set theory refers to that initial, kind of intuitive approach.
Yeah.
Where we think, oh, any describable collection can be a set.
Okay.
That makes sense, right?
Yeah.
But it turns out that this unrestricted freedom
Yeah.
leads to some serious contradictions.
Oh, no.
Like the famous Russell's paradox.
Okay, Russell's paradox.
Right.
I've heard of this. Tell me more.
All right, so imagine a set of all sets that don't contain themselves.
Okay, it seems pretty straightforward.
Right, a harmless definition.
Yeah.
But here's the catch.
Oh.
Does the set contain itself?
If
If it does, then it shouldn't,
right, because of the definition.
according to its own definition.
Yeah.
But if it doesn't, then it must.
Oh my gosh, my brain.
Right?
It's like a pretzel.
It's a self-contradictory loop.
It's like a philosophical black hole.
Exactly.
Yeah.
So Russell's paradox and other similar paradoxes, they showed mathematicians that this naive set theory needed some rules,
Some boundaries.
some safeguards to avoid these logical pitfalls.
Right. So it's like a game.
Yeah.
You need rules.
You need rules, exactly.
Right.
And that's where axiomatic set theory comes in.
Axiomatic set theory.
Yeah.
So that's where we start setting some rules.
Exactly. We're setting rules for the game of sets.
Okay.
So the ZFC axioms, named after Ernst Zermelo and Abraham Frankel,
Okay.
provide a solid foundation for set theory.
Okay.
A set of rules that help us avoid those paradoxical traps.
So this is like we're getting rid of naive set theory.
Yeah,
We're bringing in the rule book.
exactly. We're getting serious now.
Okay.
So these axioms are really, really important.
And how does this connect back to philosophy, though?
Well, think about it.
All right.
Philosophers are always trying to figure out, what are the most basic assumptions?
The foundation.
Yeah, the foundations.
Yeah.
They're trying to identify those fundamental principles that we can use to understand the world.
Okay. Yeah.
And in a way, set theory faces the same challenge.
Okay.
How do we define the basic rules of the game
Right.
to make sure that the system is consistent and logically sound?
So these ZFC axioms.
Yeah.
It's like the philosopher's toolkit.
Exactly.
It gives them like the building blocks to really understand sets in a way that's not going to break.
Yeah, that's not going to lead to contradictions or paradoxes. We
Right.
want to make sure everything's solid.
So we've got our rule book, we've got our toolkit.
We're ready to go.
Let's keep going. I'm ready for more.
All right.
Okay, so we've got these axioms, these ground rules to keep our set theory, from going off the rails into paradox land.
Right. Keep us grounded.
But where does it lead us?
Yeah.
The Stanford Encyclopedia mentioned this idea of the universe of sets,
Right.
which sounds almost mystical.
Yeah, it does have kind of mystical air to it.
Like, what is this universe of sets?
Well, the universe of sets, which we denote by V,
Okay.
is one of the most, I think, mind-boggling ideas in set theory. It's the idea that we can build an entire model.
A model.
Yeah, of everything.
Everything. Wait, hold on a second.
Yeah.
Are we talking like all of reality?
I mean, that's the big question.
Like
right?
from sets?
Yeah, can we model everything using just sets as the building blocks?
That seems like a pretty big claim.
It is, and it raises a lot of philosophical questions
Yeah.
about, what it means for something to exist. But let me explain how this V comes into being.
Okay.
It all starts with the simplest thing,
Okay.
the empty set.
The empty set.
A set with absolutely nothing in it.
Nothing. Okay.
It's like the ultimate blank slate
Okay, so we're starting with nothing.
with nothing.
How do you build a universe from nothing?
Well, this is where the magic of set theory comes in.
Okay, let's see it.
Remember the power set axiom?
Kind of?
It says that for any set, you can form a new set
Yeah.
containing all of its subsets.
Okay.
So even though the empty set has nothing in it,
Yep.
it does have one subset itself.
Right, okay, so it's a set containing the empty set.
Exactly.
That's
So the
all.
power set of the empty set is a set with one element.
Right, it's like something's coming from nothing.
Yeah, something from nothing.
Okay.
And this is just the beginning.
Oh, there's more.
Oh, yeah, there's a lot more.
Okay, all right.
We keep repeating this process using what's called transfinite recursion.
Transfinite recursion?
Yeah, a fancy term.
Okay.
But all it means is at each step, we take the power set of everything we've constructed so far,
Okay.
and this creates a new level of sets.
So we start with nothing,
Yep.
and we've got the set containing nothing. Then we get sets containing those sets,
Exactly.
and so on, forever.
Forever and ever.
It's like sets all the way down.
It's an explosion of sets.
An infinite explosion of sets.
Exactly. And as we keep climbing this infinite ladder, we eventually reach V.
The universe of sets.
Yeah, universe of sets.
Okay.
This cumulative hierarchy, it contains every possible set.
Every possible set.
Yeah, that can be constructed from the ground up
Okay.
using the axioms of set theory.
So are we saying that everything that exists,
Yeah.
from the tiniest particle to the largest galaxy, can be represented as a set in this V?
That's the big philosophical question, right?
Yeah.
It really challenges us to think about what it means to exist.
Yeah.
Is everything ultimately just sets and their relationships?
Okay.
Or are there things that go beyond this set theoretic framework?
It's a lot to wrap your head around.
It is. It's a deep metaphysical question.
It is. And I'm also kind of wary, of any theory that claims to explain everything.
Right.
And the Stanford Encyclopedia, they also talk about this thing called the reflection principle,
Yeah, the reflection principle.
which seems to suggest that even if we could understand this whole V, this universe, it wouldn't give us the ultimate truth.
Right. It's a really fascinating idea.
So what's going on there?
So the reflection principle, it says that any true statement
Okay.
about the universe of sets
Yeah.
is also true in some smaller level within this hierarchy.
So it's like we're seeing echoes
Yeah, like reflections.
of truths at different levels.
Exactly. So even if we could understand the entirety of V,
Yeah.
any truth we found there,
Mhm.
it wouldn't be unique to that ultimate level.
It would be a reflection of some other truth lower down.
Right, in a smaller, simpler part of the universe.
So it's like, is there even a single ultimate truth then?
That's the question, right?
Yeah.
Does it even make sense to talk about an ultimate truth?
If everything's just a reflection of something else.
Yeah, it really pushes us to think about the limits of what we can know.
Yeah. So it's like we're looking into a philosophical hall of mirrors.
It is. It's truths echoing and bouncing back and forth at different levels of reality.
It's a lot. But let's shift gears for a second.
Okay.
We've been talking a lot about like the philosophical stuff.
Mm-hmm.
But what about the connection to, the rest of math?
Right.
The Stanford Encyclopedia talks about this foundational role
Mm-hmm.
of set theory in math.
Yeah.
But I'm having trouble seeing how, this abstract world of sets
Yeah.
connects to the more concrete world of numbers, equations, shapes.
Right. How do we get from these abstract sets to the stuff we actually work with in math?
Yeah, exactly. Help me connect the dots here.
Well, that's where set theory shows its real power.
Okay.
It turns out that pretty much every mathematical object we deal with can be constructed using sets.
Really? So even something like a number can be built from sets.
Even numbers,
Okay.
it might seem strange. But yes, we can define numbers in terms of sets.
Okay. How does that work?
So for example, 0, we represent that as the empty set.
The empty set. Okay.
The number 1 is represented by the set containing the empty set.
Okay. So it's getting a little more complex.
Yeah, it's building up.
Okay.
2 is the set containing the empty set and the set containing the empty set.
It sets all the way down again.
It is. It's a beautiful, elegant definition.
Okay. So we're building numbers from the ground up,
Exactly.
starting with nothing.
Yep.
And then just adding more and more sets to represent each number.
It's a kind of creation myth for numbers.
I like it. A mathematical creation myth.
Yeah.
Okay. So we've got natural numbers. What about other kinds of numbers?
Oh, we can go further.
Okay.
We can define integers, rational numbers, real numbers, even complex numbers.
All with sets.
All with sets.
Wow.
And we can even go beyond numbers.
Okay.
We can define things like functions, relations,
Mm-hmm.
algebraic structures, topological spaces,
All using the language of sets.
all using sets.
So that's like this, like a universal language.
Exactly. It's the foundation of all of math.
It unites everything.
It unites everything.
Okay, so that's pretty amazing.
It is.
But if set theory is the foundation,
Yeah.
and we've already talked about how it has these unprovable truths.
Right, like the continuum hypothesis.
Yeah, the continuum hypothesis.
Yeah.
What does that say about math itself?
That's the big question.
Does it mean that math is not as certain as we thought?
Well, it certainly challenges our view of math as this realm of absolute truth.
Yeah.
It leads us into this really interesting area called metamathematics.
Metamathematics. Okay, we're
Oh.
going meta.
Going meta, yeah.
All right, tell me more.
So metamathematics is where we step back
Okay.
and look at math itself.
Okay.
We examine its methods, its assumptions, its limits.
So we're not just doing math.
Right.
We're thinking about what it means to do math.
Exactly. We're thinking about math.
That's a lot of thinking.
It is, but it's really important because it helps us understand the nature of math.
Okay.
And this is where Gödel's incompleteness theorems.
Right. Gödel, he showed that there are always going to be true statements that we can't prove.
Exactly. He showed that there are inherent limits to what we can prove.
So even in a system as rigorous as set theory,
Yeah.
there are going to be truths that we can't capture.
There are always going to be things that escape our grasp.
That's kind of unsettling.
It is. It's unsettling, but it's also exciting
Okay, how is it exciting?
because it means that there's always more to discover.
There's always more.
There's always another mystery around the corner.
Okay, so earlier we were talking about the continuum hypothesis
Mm-hmm.
and how it's undecidable.
Right.
So is Gödel's work, does that suggest that the continuum hypothesis might be one of these unprovable truths?
That's a great question.
Yeah.
And it's one that's been at the heart of the debate.
So are we just stuck?
Well, not necessarily. The undecidability of the continuum hypothesis.
Yeah.
It's opened up a lot of possibilities. And it's led to some really fascinating developments in mathematics.
So you're telling me that this undecidability,
Yeah.
this is a good thing.
In a way, yeah, because think about it. If the continuum hypothesis were provable or disprovable,
Okay.
it would be a pretty straightforward matter, right?
Yeah.
We'd either know it's true or false.
And that would be it.
End of story.
Okay.
But this independence,
Yeah.
it forces us to ask deeper questions.
Oh.
It suggests that there might be multiple mathematical universes.
Wait, hold on. Multiple mathematical universes.
Yeah, it's a powerful idea.
That sounds like science fiction.
It does, but it helps us understand the implications of the continuum hypothesis.
Okay.
It challenges this traditional view of math as a single set of absolute truths.
Okay.
It opens up the possibility of a mathematical multiverse.
A multiverse.
Yeah, where different axiomatic systems lead to different mathematical realities.
So we're not just exploring a fixed mathematical world.
Right.
We're creating different possible worlds
We're actively shaping the landscape of math.
through our choices about axioms.
Exactly, and the continuum hypothesis has become a test case for different philosophies of math.
Okay, so it's not just about the answer.
Right.
It's about how we think about the question itself.
Exactly. It forces us to confront some very fundamental questions about what it means for something to be true in math.
This is getting pretty deep,
It is. It's deep stuff.
but I'm ready for more. Let's keep going.
All right.
All right, welcome back to our deep dive into set theory.
Yeah, it's been quite a journey.
It has. We've been through infinity,
Paradoxes,
paradoxes, foundations of math,
the whole shebang.
and now we're finally tackling the big one.
The big one.
The mystery that's been hanging over our whole discussion,
The continuum hypothesis.
the CH.
Yeah, the CH. It's a question that's baffled mathematicians for over a century.
So, just to recap,
Mhm.
we know there are different sizes of infinity.
Right.
The set of all natural numbers, infinite. Set of all real numbers, also infinite.
Infinite, but bigger.
But bigger, right?
Yeah.
And the continuum hypothesis asks,
Is there anything in between?
yeah, is there an infinity that's bigger than the natural numbers but smaller than the real numbers?
Or there's the only two options.
Are those the only two rungs on the ladder?
Exactly.
And the answer is,
Drumroll.
we still don't know.
We still don't know.
It's incredible.
I know, right? It's like set theory gives us this huge puzzle and then takes away a piece.
Yeah, it's a real head scratcher.
It's a big one.
So the Stanford Encyclopedia, they point out that the CH is independent of the standard axioms of set theory.
Right, those ZFC axioms.
Right, the ZFC axioms. So,
Independent? What does that mean?
yeah, what does independent mean? Does that mean we can just, like, add it as an axiom if we want?
Not exactly. Independent means we can't prove it,
Okay.
but we also can't disprove it.
Using ZFC.
Using ZFC, right?
So it's like the tools we have,
Yeah.
they're not enough.
They're not powerful enough to figure this one out.
So are we just stuck?
Well, not necessarily,
Okay, good.
because this undecidability of the CH, it's opened up a whole world of possibilities.
Okay, so undecidability is a good thing.
In a way, yeah, because if we could prove or disprove it, it would be kind of boring, wouldn't it?
I guess so.
It would be like, oh, okay, we know the answer, end of story.
Yeah, case closed.
But this independence, it makes us think harder.
Okay.
It makes us consider the possibility of multiple mathematical universes.
Multiple universes, again with the universes.
I know, it's a wild concept.
It's a wild concept, but I'm following you.
So it's like there might be different versions of math
Okay.
where the CH is true in some
Okay.
and false in others.
So it's not about finding the one true answer.
Right.
It's about understanding that there might be many answers.
Depending on which axioms you choose.
So it's like we're not just discovering math,
Mm-hmm.
we're creating it.
In a way, yeah, we're shaping the landscape of mathematics.
That's a pretty powerful idea.
It is. It's a very powerful idea.
So the continuum hypothesis, it's a test for different philosophies of math.
Exactly.
It makes us ask, what does it even mean for something to be true in math?
Yeah. Is there one absolute truth?
Or are there many truths?
It's a fundamental question.
This is big.
It's big stuff.
So where do we go from here?
Well, the search for an answer to the CH continues.
Mm-hmm.
Some mathematicians, they're looking for new axioms
Okay.
that can settle the matter.
So they're not satisfied with this undecidable verdict.
Some aren't. They want a definitive answer.
So they're trying to change the rules of the game.
Yeah, they're looking for new tools to solve the puzzle.
Okay, and one of the big players in this was Kurt Gödel,
Right, Gödel.
the guy from the incompleteness theorems.
The same one.
So what did he think about the continuum hypothesis?
Well, Gödel, he believed that the CH was false.
Okay,
And he actually built a model of set theory.
he built a whole model.
Yeah, it's called the constructible universe.
The constructible
They're
universe.
denoted by L.
Okay, L.
And in this model, the CH is false.
So he created a whole mathematical world where the CH doesn't hold.
Exactly, and it's a perfectly consistent world.
So it's possible that the CH is false,
It's possible, but...
but we also can't disprove it,
Right, and that's where Paul Cohen comes in.
right? Another name.
He developed this technique called forcing,
It's forcing, okay.
and he showed that you can also build models where the CH is true.
So we have these different models, different universes,
Yeah.
where the CH can be true or false.
It all depends on which axioms you choose.
This is pretty mind-blowing.
It is. It really challenges our understanding of math.
So what's the answer?
That's the million-dollar question, and we still don't have a definitive answer.
But maybe the journey is more important than the destination.
I think that's a good way to look at it.
It's the exploration, the questioning.
That really expands our understanding.
We started with this question about infinity,
Yeah.
and we ended up exploring the nature of truth itself.
Set theory is full of surprises.
It really is. So to wrap things up, our deep dive into set theory has shown us that math is more than just numbers and equations,
It's a way of thinking, a way of understanding the world.
and it's deeply connected to philosophy.
Absolutely. You can't separate the two.
So keep questioning, keep exploring, and keep diving deep.
That's what it's all about.
And on that note, we'll say goodbye for now.
See you next time.